Yeah, so I'm going to talk a little bit about a study where we are essentially trying to integrate the radar and the optical together. So our overriding goal in this sort of program, because it's not really just one project, it's several projects, is to try to estimate luminous efficiency. And we want to do that at a range of sizes for a range of magnitudes, with the ultimate goal of trying to have an independent model for luminous efficiency. So when we see an optical measurement, we can get a mass. That's really what we want to do. So our study motivation here is, in a generic sense, the meteoroid mass scale is uncertain. Much of our meteoroid mass measurements come from optical observations. So if we have optical observations alone, we always have this magical missing parameter, the luminous efficiency, or tau, which has been the bane of meteor science for 50, 60, 70 years. So in our particular case, what we're trying to do is we want to get an independent estimate of mass using the amount of electrons that are produced, so the plasma production. So that means we're going to be employing radar. And we want to be able to also make use of luminous efficiency. So we're going to look at photons. But again, we have to remember there are some fundamental underlying physical coefficients. That is, how many electrons are produced per atom that's ablated, and how many photons that are produced per atom that's ablated, and affiliated properties like velocity, mass, height, and so on. So there are a variety of ways you can approach this. One way or another, you need two methods that produce independent estimates of mass. But again, our approach in this sort of program is to make use of radar measurements from SYMOUR and correlate them with optical measurements. And so here I'm going to talk about one set of correlated measurements where we use very sensitive cameras, so I'll talk about in a second. But I should say that because SYMOUR actually operates at 3 frequencies simultaneously and makes multi-static observations, so that in each case you have a trajectory, you have, as Gunter pointed out, a polarization angle, so you understand the scattering geometry on a per echo basis. We actually are correlating all of our optical instruments with radar all the time. So every night, our all sky cameras, when they detect bright meteors, we cut out all the radar data. Fainter meteors, GMN cameras, all get synchronized. So there's actually a huge data set of simultaneous optical and radar measurements. And I'm really just drilling down into one particular data set. And so again, one of the motivators here is we have these two unknowns: ionization efficiency, how many electrons you produce per atom that's ablated, and luminous efficiency, what fraction of the photons, the total energy that's released by a meteor is released in the form of photons. And one of the sort of starting points here is to recognize that ionization efficiency in general is a bit simpler physics, and so arguably has better laboratory calibrations and is more robust. So we have a pretty good idea of how many electrons are produced for a given composition. I'll talk a bit more about this. But what I'm going to try to do is leverage the notion that this is a bit better known than luminous efficiency. So we're going to try to make measurements where we can leverage that better understanding of beta to then invert for and get measurements of tau. All right, so how does this all work in an observational sense? So here's a really bad image that I picked up very quickly that just shows these are stars. The image here is about 15 by 20 degrees. Each little blue dot here is an individual video frame where we have the meteor. So here's actually the meteor in this case. And what we do is we have timing and we have direction for the interferometer from the radar. And this optical station is co-located with the radar. It's about 30 meters away from the radar. Of course, from the astrometry, we can get the position of the meteor. And so what we try to do is we identify radar echoes. So this is range in this direction. This is time. And this little tiny blip right here actually is the little segment of the meteor trail right here. How do we know that? Well, we can check the timing. We can check the interferometry position and see that those agree. We also can use the fact that, in fact, the optical measurements are made at 2 stations. And so all the optical meteors we also have optical solutions that are totally independent of the radar. And so we insist that the optical solutions are good enough that the equivalent specular point of the optical trail, which is 90 degrees from the radiant, is within essentially a degree of what the radar specular point gives us. So we have 3 independent ways of making sure we're looking at exactly the right part of the trail, so we can say this is where all the photons are coming from. So here's an example where we actually, this is the meteor here, this is the light curve of the meteor. You can see it was getting fainter. And by the time we actually see it here at the specular point, it was about 7th magnitude. And what's nice about this, you'll notice the SYMOUR echo is not really, really strong. And in fact, we finally have cameras that in the way they're configured, get down well into the underdense regime. And in fact, some of our cameras now exceed the sensitivity of SYMOUR, at least in the direction we're looking. So we finally have cameras that can push right down to the background level of the radar. So at the end of the day, we can look at the photons produced here, compared to the electrons produced here using the scattering model that Günther just talked about, and we can try to relate the electron production to the photon production. So just a word or two about the facilities, what we're actually using. So the optical facilities are part of the Canadian Automated Meteor Observatory, which are 2 automatic observatories that have a bunch of different instruments. So they have this mirror tracking instrument, which many of you have probably seen over the years, where we talk about, we call the narrow field instrument, but I'm actually talking about a different set of cameras. These are electron multiplied CCDs produced by Nuvu. There are a pair of each of them at 2 sites. The sites are here at Elginfield and Tavistock. Tavistock is also where SYMOUR is located. All of the cameras are pointing to this common location, and SYMOUR is also producing, of course, a broad beam that also interrogates this area. So as a result, in this common volume, we can get multiple optical measurements, trajectories optically, and simultaneous radar measurements. So the Nuvu EMCCDs run at about 30 frames a second, or GPS stamped. The limiting detectable meteor magnitude is around +8, although we're only complete to about +5 to +6. And the EMCCDs use a very nice cluster detection matched filter algorithm that was developed by Pete Gurel, which gives us a great deal of fidelity in terms of capturing very faint meteors, which we can then correlate back with SYMOUR. So this is just showing the EMCCD meteor distribution. So here's the peak brightness in the G band. Here's our detection. This is essentially a survey over a period of the last 3 or 4 years. And we're complete down to about 5th magnitude. We see some meteors down to 7th or even 8th magnitude, although there's not very many of those. But in the individual frames, this is the peak brightness. In the individual frames, we can often get 9th or 10th magnitude portions of the trail being detectable on these instruments. And they're looking at a 20 by 15 degree field of view. And of course, again, for our purposes, the really important point here is that we're right down to almost the sensitivity limit of SYMOUR, so we can see those really nice underdense echoes. So what about SYMOUR? So Canadian Meteor Orbit Radar, we have 3 systems that have this Jones-style interferometry configuration. So it lets us get 3 independent estimates of the interferometry at 3 different frequencies, 17, 29, and 38 megahertz. All 3 radars are slaved together, so they see the same pulse at a given time. The 29 megahertz system, there are also 6 outlying stations within about 22 kilometers, which are also synchronized. And that allows us to do time of flight measurements. So when we have a meteor occur, we have the direction from the main site, and then we have all these other specular points that allow us to do time of flight measurements to give us a speed and to give us a direction. And of course, at SYMOUR as well, we have one of the camo sites, so we're looking optically at the same place. So if you look at the whole sky and you look at the gain pattern of the SYMOUR antenna, most of our power is directed directly overhead because these are 3-element vertically directed Yagis. But the field of view for our optical systems is just this little patch here. It's actually fairly near the zenith. So we are seeing sort of as faint as we can get with SYMOUR, but we're still getting some reasonable collecting area. And so it's this common volume that we're interrogating for most of this work. So very briefly, in a little bit of detail, what we're actually doing, what we measure is from the radar echo, we get the electron line density. From the optical measurement, we get the peak brightness at the specular point. And of course, we have the velocity from the optical cameras and multiple radar techniques, so we can get a velocity and an uncertainty with the velocity, because that turns out to be a big source of error in our measurements. We also have to make an estimate of the sort of mean atomic mass of the meteoric atoms, which in general we have a reasonable guess at, although it's not always uniquely constrained. But with just these measurements, we can measure uniquely the ratio of the ionization efficiency to the luminous efficiency. And that's essentially what we're doing. So we get I from our camera, we know V from our various measurement systems. we have to get electron line density. That turns out to be the more challenging part. Gunter has sort of outlined exactly how we do that by looking at the peak power, applying a scattering model, the polarization angle, and so on. There's still uncertainties with this, but the more frequencies we have, the better we're able to constrain this. So for much of the data set we're going to talk about, we actually have 3 frequencies that measure the echo, and then we tried it with a model to match those amplitudes to a unique estimate of electron line density. How do we know that the radar echo and the meteor echo and the optical meteor measurement is the same? Well, it's not totally trivial because you can get spurious associations. We require a common range to the specular point. That is, the 2-station optical has to agree with the radar range. We have to be within a few degrees on the sky, which is, a couple of Fresnel zones, but it accounts for the fact that the radar phases do drift. The phases are not perfect. We don't have an automatic calibration every day, so we have to allow for some uncertainty there. And of course, our best estimate here is timing, because we have GPS timing on both the radar and the cameras. We have to have all of these agree to within 1/10 of a second. So if all 3 of these conditions are met, we declare that these are in fact common meteors. So as I said, the most challenging part is to try to get this electron line density from the specular scattering. Again, Gunter has described this in great detail. I'll just say that for our initial work, we're sort of assuming a model for the trail radius, but we're working on this idea of using all 3 frequencies to get a unique independent estimate per echo of the trail radius. We put in an ionization efficiency, we measure the power, and then with the polarization angle known, we can get a reflection coefficient, and that ultimately can lead back to a unique estimate of Q. I would just say that when it comes to ionization efficiencies, what you'll notice is it's very, very low at low velocities. And this just reflects the fact that there's not much energy at these low speeds. And then you get up to higher speeds and you're almost always producing at least 1 electron on average per collision at those high speeds. So as I mentioned, this work that we're doing is part of sort of a broader program. And we already published the first part of this program a year or so ago. And what we did is we looked at all low velocity EMCCD events. So this is the meteor speed as measured by the EMCCD. And this is the luminous efficiency in percent. So this is 1%, 10%, 100%. This is the radiant intensity at the specular point measured by the EMCCD. So down here, this is 8th magnitude, and up here, you're talking about things that are approaching 4th and 5th magnitude. We were only able to identify 30 low speed events that met all our criteria and for which we had good radar data. And each of the points here represents an individual meteor measurement where we got the Q over I and could measure tau uniquely using the beta from the laboratory, the measured beta. And there's some estimates here. This tau is from a whole bunch of different previous literature works. And you see there's a big range. And what you'll notice is we have quite a bit of scatter. There is a little bit of a trend here that the fainter the meteor, the lower the luminous efficiency appears to be. And that's a trend that previous people had suggested or discussed. But our questioning here was, is this variation really due just to the luminosity, or is it due to changes in composition? Because of course, these are all from different sources. These are all low velocity meteors. So our second part of this program was to try to understand how does tau change with speed, so expand the speed range of our tau measurements. Are variations in the tau due to compositional differences, or is it luminosity, or both? And so what we were hoping to do here, basically, or what we're planning to do, is to look at meteors that are above 20 kilometers a second, and in particular are from specific meteor showers. So the notional idea here was, well, if I'm looking at 8 or 10 meteors from the Alpha Capricornids, arguably there's less compositional difference than if I was looking at 8 random meteors from the same velocity band. At least that was the intent here. So we were able to find an additional 60 or so shower meteors that met all those criteria and were seen optically and with radar. And among those, we had a fair number of events from 4 different showers: the Alpha Capricornids, North Delta Aquarids, Northern Iota Aquarids, and South Delta Aquarids. So let me first show you sort of the overall data set. So just to start off with, notice this is beta over tau. So this is really the fundamental measurement. And if you put in different values of luminous efficiency, you get for the assumed beta, assuming a chondritic composition, you get these different lines. So this is a very, very low luminous efficiency of 0.1%. This is 1%, and then this is 10%. And this part 1 of the study is basically these guys over here. Everything to the right are these sort of new events. which are from these 60 different shower meteors. You can see there's still a lot of variation. I can transform this into something a little bit more familiar, that is the luminous efficiency. So here's my luminous efficiency. Here's my older events as a function of velocity and also luminous power. So up here, I'm sort of at the 7th to 8th magnitude, and here I'm at 3rd to 4th magnitude. And you'll see there still is a trend that the higher luminous intensities tend to go with higher luminous efficiencies. The fainter meteors with lower photon production seems to have lower luminous efficiencies. And I'm showing here just a couple of additional notional measurements. And you get from this that actually the earlier models are not terribly bad. I mean, given all the scatter we have,
yeah, I don't know how this
it's not a
so I have something to
not an outrageous sort of fit.
Adam, yeah.
Joe, could you please mute your microphone? And Peter, you have 3 minutes left.
Come on, it's on.
Okay, very good. So this is actually my second last slide. So this is just showing our luminous efficiency as a function of luminous intensity for our different showers. And again, unfortunately, we don't have large number statistics. You might be able to hand wave your way away and say, well, yeah, as I go to higher luminous intensities, the luminous efficiency increases, but the number statistics here still are not terribly convincing, unfortunately. What we need is a much larger number of individual shower events to really get something that's going to be meaningful. So this is still a work in progress. Our summary to this point is, so in this program, we've measured about a total of around 80 events from 12 kilometers a second up to 65. We find an average luminous efficiency of about 0.9%, a median around 0.5%, but with a significant range. And this is all appropriate to meteors between about +4 and +8, sort of producing underdense meteor echoes. There does still appear to be a clear trend of larger luminous efficiency with luminous power. And in fact, if you use the earlier work that Rob Werrick derived as part of his PhD thesis for the median power of the events in our sample, you actually get a pretty reasonable fit for the luminous efficiencies we see. Again, with the idea that there's quite a bit of scatter. The showers we see still show considerable scatter, so it's probably not just compositional variations. There probably still is a trend with power, but we still need larger number statistics to understand that. And I will say the sort of next step in this project is we have about half of our meteor shower events have well-fit triple frequency measurements. That'll give an independent estimate of Q, and an initial analysis of this shows that most of our luminous efficiencies tend to be even lower than what we're showing here when we use all three frequencies combined together. And I'll just end with an out-and-out advertisement. Anybody who's interested in doctoral or master's studies, or if you're looking for a postdoc in the next couple of years, the Meteor Group is hiring. So we'd love to hear from you if you're interested in meteors and projects like this. So thanks very much.